The most intense battles in aviation don't happen in the sky. They happen deep inside the engines that power it. While aircraft manufacturers fight for headlines, a quieter war is being waged between the companies that build the machines hanging under the wings. And right now, that war has a clear front line. On one side is Rolls-Royce, pushing a radical new vision with its UltraFan program. On the other is General Electric, defending its dominance with the mighty GE9X. This isn't just a comparison of engines. It's a clash between two completely different philosophies about the future of flight. Rolls-Royce didn't arrive at this moment by accident. Its story begins more than a century ago, long before commercial aviation even existed. During the First World War, the company entered aerospace with the Eagle engine, powering British bombers and long-range aircraft at a time when reliability meant survival. That reputation only grew in the Second World War, when the Merlin engine became legendary, driving aircraft like the Spitfire and Hurricane and shaping the outcome of the Battle of Britain. From the very beginning, Rolls-Royce wasn't just building engines. It was building trust. When the jet age arrived, that trust was tested. Propellers vanished. Jet propulsion rewrote the rules. Rolls-Royce adapted again, developing early jet engines that spread across the world, even powering aircraft beyond Western borders. But the company's most defining moment came later, with an engine that almost ended everything. In the 1960s, the RB211 program pushed engineering limits too far, too fast. Costs spiraled. Development stalled. Rolls-Royce collapsed financially and was nationalized. Yet out of that disaster came one of the most important breakthroughs in aviation history, the high-bypass turbofan. It was quieter, more efficient, and perfectly suited for commercial flight. That single idea became the foundation of modern air travel and saved the company from obscurity. Still, even that breakthrough had a flaw most passengers never think about. Inside every jet engine, compressors, turbines, and the massive front fan all have their own sweet spots. Most manufacturers accepted a two-spool design as a compromise. It worked well enough, but as engines grew larger, the compromise became painful. Fans spinning too fast pushed blade tips towards supersonic speeds, creating noise, stress, and efficiency losses. The industry accepted those limits. Rolls-Royce didn't. Instead of accepting compromise, it broke convention. Engineers introduced a third shaft, separating the fan from the other rotating systems. This triple-spool design allowed each section of the engine to run at its optimal speed. Noise dropped. Efficiency improved. Mechanical strain decreased. It was complex and risky, but it worked. That architecture became the backbone of the Trent engine family, powering long-haul aircraft across the globe and cementing Rolls-Royce's dominance in wide-body aviation. For years, the Trent engines ruled the skies. But pressure kept building. Fuel prices climbed. Environmental scrutiny intensified. Airlines demanded more efficiency without sacrificing reliability. Incremental upgrades were no longer enough. Rolls-Royce needed another leap, not a step. That leap began quietly with the advanced programs. Engineers tore the engine apart conceptually, redesigning cores, airflow, and materials from scratch. Additive manufacturing became central. Tens of thousands of components were 3D printed to reduce weight and complexity. Ceramic matrix composites replaced traditional metals in the hottest sections, allowing engines to run at far higher temperatures without damage. These weren't marketing tweaks. They were fundamental changes. The results were staggering. Compared to earlier Trent engines, the technology promised efficiency gains approaching 25%. In aviation terms, that's enormous. It's the difference between profit and loss on long-haul routes. And this was only the beginning. When Rolls-Royce revealed UltraFan, attention immediately shifted to its size. With a fan diameter reaching 140 inches, it became the largest commercial turbofan ever built, even larger than the GE9X. Those massive fan blades are made from carbon composites with titanium leading edges, cutting hundreds of kilograms from the engine's weight while allowing a much higher bypass ratio. UltraFan pushes beyond 15:1, a figure once considered unrealistic for engines of this class. But size isn't the real shock. The gearbox is. UltraFan introduces a massive reduction gearbox that allows the fan to spin slower while the turbines rotate faster, each at their ideal speed. This reduces noise, improves efficiency, and slashes fuel burn. Gearboxes at this scale are brutally difficult to engineer, facing extreme torque and heat. Rolls-Royce didn't take this gamble lightly, but by doing so, engineers were able to reduce turbine stages from 10 to just 6, simplifying the engine and cutting even more weight. On paper, UltraFan doesn't chase raw power records. Its thrust tops out around 100,000 pounds. By comparison, the GE9X pushes past 110,000 pounds and once set a record at 134,000. But this comparison misses the point. UltraFan isn't built to win a tug-of-war. It's built to win the long game, thanks to its higher bypass ratio, advanced materials, and geared architecture. UltraFan is designed to deliver up to 20% fuel savings compared to today's largest engines, including the GE9X. Over an aircraft's lifetime, that translates into billions saved and massive reductions in emissions. And the quieter operation addresses one of aviation's most persistent challenges: noise near airports. Then there's sustainability. UltraFan has already been tested, running entirely on 100% sustainable aviation fuel, not blends, not partial substitutions, full SAF. That alone could reduce life-cycle carbon emissions by up to 80%. In an industry racing toward stricter environmental targets, this capability changes everything. Of course, no engine flies without proving itself. UltraFan still faces years of testing and certification. Rolls-Royce plans flight tests using a modified Boeing 747, gathering mountains of data before any commercial launch. Timelines point to the late 2020s or early 2030s, assuming no surprises emerge. That raises the final, unavoidable question: where will UltraFan fly? Officially, nothing has been announced, but speculation is everywhere. A next-generation wide-body, a revival of ultra-large aircraft, or an entirely new platform yet to be revealed. Rolls-Royce has confirmed UltraFan is scalable, covering thrust ranges from narrow-body jets to the largest aircraft imaginable. And that's what makes UltraFan so dangerous to competitors. It isn't just an engine, it's a platform, a foundation that could quietly replace the Trent family and redefine how aircraft are designed for decades to come. GE may still hold the crown for raw thrust, but Rolls-Royce is aiming for something bigger than power. It's aiming for efficiency, sustainability, and control of the future. And in aviation, the company that defines the future usually wins long before passengers ever notice. That future-focused strategy is exactly why UltraFan has made competitors uneasy. Because while raw thrust grabs headlines, airlines don't make purchasing decisions based on bragging rights. They care about cost per seat, fuel burn over decades, maintenance cycles, and how well an engine fits into an industry that's being reshaped by environmental pressure. And this is where UltraFan quietly shifts the balance. The higher bypass ratio isn't just a technical flex. It directly translates into smoother airflow, lower exhaust velocity, and reduced noise footprints around airports. That matters more than ever. As communities push back against expansion and regulators tighten noise limits, an engine that's naturally quieter doesn't need as many compromises later. It starts with an advantage baked in. Maintenance is another hidden battleground. Fewer turbine stages mean fewer parts exposed to extreme heat and stress. Advanced materials like ceramic matrix composites don't just improve performance, they extend life cycles and reduce inspection intervals. Over tens of thousands of flight hours, those differences add up to real money. Airlines don't see an engine, they see spreadsheets, and UltraFan was clearly designed with those spreadsheets in mind. Then there's adaptability. UltraFan isn't locked into a single role. Rolls-Royce has openly described it as a family of engines, not a single product. The same core architecture can be scaled up or down, adjusted for different aircraft sizes, and tuned for different mission profiles. That kind of flexibility gives airframe manufacturers options they haven't had in years. Instead of designing an aircraft around an engine, they can start imagining engines that evolve with the aircraft. Meanwhile, General Electric's approach with the GE9X reflects a different priority, built specifically for the Boeing 777X. It delivers unmatched thrust and impressive efficiency gains over its predecessor. It's a powerhouse, optimized for one of the largest twin-engine aircraft ever built. But that specialization also limits its reach. GE9X dominates its niche. UltraFan is trying to reshape the whole field. The contrast couldn't be clearer. One engine pushes the limits of power. The other pushes the limits of efficiency and sustainability. Neither approach is wrong, but as fuel costs fluctuate and climate targets tighten, the balance of what matters most is shifting. This is why UltraFan's ability to operate on 100% sustainable aviation fuel is such a strategic advantage. With long-term policy reality,